I will use it to prove my beliefs, which is that the Illuminati is controlling everything that exists, whether we
Take
know
a
it or
cookie.
not.
One cookie.
Those are my
I think you have to
actual,
specify Hey, Devin, how are you?
those are my actual beliefs, but I think it's important to state them.
can't see.
Okay, we were gonna make a list of the 5 most important numbers, like not jokingly, like actually, what do you think are the 5 most important numbers that you have come across in your mathematical studies?
Like transcendental or like.
Sure, any numbers that you have thought, like, have come up frequently
Zero.
enough?
E.
Oh, what's that?
Zero.
0, that's a good one. I'm just gonna do one at a time. So why is 0 important?
Because it's not really.
Because it represents the lack of number.
Okay.
That
So
was so nice.
That was so hot.
we can. That's done. QED. Okay. So lack of number.
Can I see another one?
I'm going to put that in quotations. One second, we're just going to make a list here. Okay, but it's also the base, we're in a base 10 number system, so adding a 0, and so you go to the next
There you go. That's
thing,
it.
right?
That was gonna be the next.
Also, I would say it's the additive identity, so it's the thing that you can add to anything and not change it, okay?
My favorite number.
Are the real numbers a
I love it when something's zero.
Are the real numbers what?
A group.
Yes, the real numbers are to T. Okay, good. Next one, I heard E.
I said pi. Can pi be next?
Pi is also one, good.
that too.
Okay, so just one second, let's just explain why is this important. Why is E important?
Because it appears in many organic science things.
We're just gonna explain it.
No, I have an explanation for E.
Oh, okay, yes.
It's also used to measure like rate of change and stuff, which is like a really important,
Yeah.
like the basis of mathematics. Not really.
Ooh.
What?
No. It's just.
Can one be one?
Okay, it's there's
Yeah, that's
infinite. Okay, this is good. Okay, pi. Why? One second. We're gonna. Yes, you're right. You're right. But let's just. Okay, pi is one. Why pi? Why is pi important?
It's delicious.
No, I'm not gonna say that.
Oh. Why is it the most important? Oh.
Okay, it's built into every. This is like one of the first like numbers you learn that is not one of the natural numbers, because this is pi is supremely important. We've seen pi a lot of times. What did you say?
One.
1. Good. 1. Why is 1 important? Well, you could say.
Because if you multiply 0 by something, the 0 takes over but 1. Like nothing changes when you multiply.
Exactly. So this was the additive identity. This is the multiplicative identity.
It's a
Good.
word?
Yep.
Multiplicative. Also, it's the divisitive.
Yeah, the multiplication and division are the same thing. Okay. Well, there's opposites of each other. We're almost on the list.
Gina's like, no, it's not.
No, I think they're this. One is the inverse of the other. So an identity one. That's like saying the subtraction identity is 0.
Yeah, but okay.
It's just a, okay.
Okay,
Anyway.
fair, fair.
Okay, we need one more. Any suggestions?
12.
No. There's no way you can
3.
justify that. Why 3?
Because it's
Negative
it
1.
appears everywhere.
Okay, -1. That's closer to what so I'm obviously looking for something specific. -1 is closer to what I'm looking for.
Negative pi.
No, not -1, but something.
I said pi.
The something of -1.
Square root.
The square root of -1. What's
That
that?
doesn't exist.
Imaginary number.
I, the imaginary number I. Okay, so this is a number. We're not going to talk. We're going to talk a little bit about imaginary numbers, but this is a number. Okay, we're going to call this
Wait,
square root of
there's only
-1.
4 out of 5 on the first, like.
Yeah, that was good. No, Justin, that was really,
80%.
really, really good. Okay, the square root of -1 basis. No, so no, I won't say basis. I'll
Of the
say
imaginary number.
for the complex numbers. Okay, so I'm just going to give you a quick. Very quick run through of where each of these things comes from. Okay, so 0 and 1, I don't need to explain to you. They're very easy. E, let me just very, very, very quickly explain where E comes from. 0 and 1 you just obtain by counting. Okay, E, where does E come from? Okay, so say it comes from the theory of compound interest. Okay, so here's how it works. Okay, so say I give you $1, okay, and I charge 100% interest for a year. So this is the template that we're using. So we're going to start with $1, 100% interest, 1 year. Okay. So what does that mean? So what that means is, so I was going to done it. If I give you $1 at the end of 1 year, how much do you owe me?
$2.
$2, right? I charge 100% interest. You owe me the exact. That was clutch, man. You owe me the exact amount I gave you. That's what 100% interest. Okay, this is not very exciting. So what that means is what I did is I only charged you at the end of the year. Okay. So what I did is I didn't compound the interest. Okay. And I'll explain what that means. So let's say end of year. Okay. End of year. So let's just say this is 1. Okay, I get $2. I'll keep away the dollar sign. I get $2. Okay, so compound twice. Okay, what does compound twice mean? That means that after 6 months, I charge you 50% interest, and then after another 6 months, I charge you 50% interest again. Okay, so what that means is. So if I give this to you on January 1st, on June 1st, you owe me $1.50, okay? And then at the end of the year, you owe me 50% of $1.50, which is $2.25. Okay, so I'm going to write this. So I'm going to say, so after 6 months, it's going to be, I'd say, okay, so let's see. So it's 1 plus 1/2, right? 1/2 of 1, you start with 1, right? So you do 50%, okay? And then times this thing plus 1/2 of it. Okay, so what does this mean? So this means after 6 months, okay, you owe me the 1 plus the 1/2 of the 1. So that's me charging you 50% interest halfway through the year. And then at the end of the year, you owe me this plus 1/2 of this, because I'm charging you 50% interest again on what I've now charged. Okay, so I can instead write this as 1 plus 1/2 squared. Is that okay? And that in this case is 2.25.
We don't have to. Sorry.
Yeah. You have a question?
We don't have to. Never mind. Yeah.
Okay.
Sorry.
We're spending this whole class on this one proof, so you can ask. Yes.
It is never mind.
But you understand what I'm doing here?
Yeah, it's the 2 goes to n, right?
Yes.
You take the limit, right?
Yes.
Yeah.
Yeah, but you're getting ahead of me.
Sorry.
So let me just do it one more time. So
Sorry.
4 times, okay? So I say 4 times, then after, we're going to do it every, 3 months, right? So after 3 months, you owe me the $1 plus, a quarter of that, okay? And then after
6 months.
6 months, right, you owe me this thing plus a quarter of this thing, right? And after another quarter, you owe me this thing plus a quarter of that, right? And after a fourth, you owe me a quarter, this thing plus a quarter of it. Or 1 plus 1 over 4 to the 4. Okay, so this is called the theory of compounding interest. It says, how many times throughout the year do I want to press the interest button, okay? Ultimately, you're charging 100% interest on the year for the whole year. Of course, this is bigger than 2, right? So this is 1 plus a quarter is 5 over 4 to the power of 4. Can someone tell me what this
25
is?
over 16.
Yeah, which is bigger than, I don't know.
It's bigger than 2.
No, it's not 25 over 16. It's 5 to the 4 over 4 to the 4. Can you just get out the calculator? Tell me what this is.
Didn't bring one.
2.5 over.
Can you just tell me what this is? Okay, let's just say, I don't know, 2.6. This is made up. It may be this, it might not be.
5 is like 625.
Whatever it is. Okay, so of course,
Less than 2.71.
if I compound now n times, okay, Donovan, you
Sorry.
Cheated.
no, it's totally fine. You get this, right?
Yeah.
So now what we want, okay, is to do what's called continuously compounding interest. Okay? That is to say, I'm charging you interest every nanosecond, I'm continuously charging you interest. It's exactly what you said. You just take the limit as n goes to infinity. You're not charging every,
Can you compute the limit? I don't know how to do it.
you most certainly can. So what we're going to compute is this.
Wouldn't that just be 1 to the infinity?
Yeah, that's what I would have thought too.
Well, we've done, how quickly they forget. We've done, first of all, this is okay, so this is there's actually a number whose definition is this, but I won't tell you what it is.
E?
Yes, this is the definition of E, okay?
Donovan's getting so ahead of everyone.
I know, you're on fire. Okay, this is the definition of E, but like you don't have to believe me, let me just show you on the board. Okay, maybe this is too, okay, I'm guessing this. Okay, so, I need to erase the cowbell thing, so.
Well, that was yesterday.
It's belated.
Okay. Remember how we do this? Limit. Right, 1 plus 1, oh, thank you. Okay, do you remember how we did this, right? We take the ln of both sides. Remember we do this? We take ln of A is equal to n, the limit.
It's
But doesn't
2.4
lawning
BTW.
something require for you to believe in the existence of E already?
Yeah.
Yeah, this limit, you can show that this limit, you can actually show that this quantity is bounded above
By E?
by 3, for example. Like, that takes a long time to show. But you're right. And you actually show that, interestingly enough, by doing this thing as a Taylor series with the binomial theorem. You know what I'm saying? So it's all, okay, but we're not going to do that. But you're right. That's a good point. You first have to show that this thing exists, and it does because you can show it's bounded. So if the thing is bounded and you can show that this is always increasing, then the limit of this thing must exist, right? Okay, so this is good. So this is allowed, right? This is legal. Okay, so if I take the ln of this whole thing, I get n times 1 plus 1 over n, or n plus 1, right? No, that was not right. Was that right? I'm sorry. So let's see. Okay, one sec. Let me try that one more time. I get ln of n approaches infinity, 1 plus 1 over n to the n, right? Which gives me of n times, yes, you're right, sorry about that. Okay, n times ln of 1 plus 1 over n, right? And so this is infinity times, right, this thing goes to 0. Infinity times ln of 1 is 0. So that's a L'Hopital's situation, right? So I can actually do limit as n approaches infinity. Maybe I'll do ln.
Wait, why is it L'Hopital? Isn't it just 0? Like, it's not 0 over 0.
It's not 0 over 0, it's infinity times 0. Which is, we don't know where it goes. So I'm going to do over 1 over n, right?
Yeah.
There's 8 cases that are not.
Okay, so now I do L'Hopital. Okay, and this is now, let's see, the derivative on the top is the derivative of the inside, which is minus 1 over n squared, times the derivative of the thing, which is 1 over 1 plus 1 over n, right? Okay, then this thing divided by minus 1 over n squared. So over minus 1 over n squared is going to cancel this because the derivative of this is minus 1 over n squared. So I just get limit as n approaches infinity of 1 over 1 plus 1 over n, which is 1. So we get ln of a is equal to 1. So a is equal to e. So this is actually the definition. This is actually the definition of E. So it's kind of it's a circuitous proof because the definition of E is this, but I've now kind of shown that this is correct, the correct definition of E. So what does this mean? E is the number which, when I give you $1 with 100% interest for a year, continuously compounding, you'll give me E, which is like $2.7 at the end. So in fact, if I'm a banker, I would rather charge you continuously compounding interest than charge you once at the end of the year. Okay? And actually, it doesn't have to be, of course you can imagine, it doesn't have to be 100%, it doesn't have to be $1. It can be, if it's $2, you multiply it by 2. If it's less than 100%, the formula is like P E to the RT or something, where this, in our case, is 100% equals 1. So you could put any, fraction, whatever. Not to be confused with like PV,
Did Euler find E?
So Euler, I think named E, but I think E exists, like people knew about the existence of E before Euler. This guy, De Moivre.
Oh, wow.
De Moivre.
It's always a French guy.
De Moivre. I think possibly knew about E before Euler. I don't know though. I don't actually know what the history. Of course, it's named after Euler. It's E for Euler. Yeah, anyway, there's E, okay? Any questions about E? So we know about 0, we know about E. I trust that you understand pi. Every circle happens to have this built-in constant. As soon as you draw a circle of course being, the definition of circles, pick any point and pick a length. take all the points that are that length away from the point. That's the definition of a circle. It just so happens that this thing comes built in with a constant called pi if you take circumference over diameter. And in fact, you can, using a similar kind of technique, I'm sure you've maybe seen this kind of thing, like you close it in a square, and then you close it in a hexagon, then you close it in a octagon, and then in the limit of these things you can actually prove like the existence of pi. Okay, that's all good. One I, we should talk about I a little bit because I is kind of maybe a little unfamiliar.